All right, class, I hope you enjoyed the Brain Games episode that you watched yesterday, or the last class that we had, that looked at how our brain puts together sensory information so that we can use it and understand it. So, today, to help introduce this unit, I'm going to go over some basic terminology for body sensations and how do psychologists use them to describe our ability to understand the outside external world around us. So I do apologize. This is going to be kind of a definition type day, but you need to know these things because it's going to relate to our in-depth studies of hearing and vision that we're going to do later in the unit. All right, so first, what we know from our bio unit way back at the beginning of the year is that part of our nervous systems are built to allow us to experience the external world. You have these sensory neurons, the afferent neurons, that are consistently receiving external signals and transforming them into neural communications so you can internally understand and interact with them. And so, what sensation means in the realm of psychology is how do we process those external stimuli into a neural signal that's usable? Right? These neural signals are then going to be sent to the brain so it can be processed and then perceived. And that's what the video you watched last class illustrated, those processing moments of how our brain puts these things together. Right, so in order for us to take an external signal and encode it into an internal neural stimuli, that stimuli needs to reach a certain threshold. All right, our external environment needs to give us a certain energy level so we can transform it into a neural signal. All right, so for example, the picture that you see here, the visible light spectrum is the only amount of light waves that humans are capable of experiencing and seeing. Right, so this is all of those rainbow colors. We'll talk about this later when we get to vision. But there are many other light waves out there that are just outside of human experiences. Versus bees, well, they can actually see more of these colors. They have the ability to see more of those infrared rays that humans just can't experience. Same thing with sound. Right, there are certain threshold frequency levels that need to be met for humans to experience it and hear it. Right? But dogs have a great sense of hearing. There are a lot of frequencies that are higher in pitch that humans can experience, but dogs can clearly hear them. Think of those like dog whistle type sounds. And so, in order for a human to experience this external stimuli, it needs to come to them in that threshold level that they can experience. And there are only certain levels that we know humans are built for processing. Right? Within that, human individual differences, and so my thresholds might be different than your thresholds. Right? This is called absolute thresholds. Right? For 50% of the time, what's the minimum stimuli you need to process that signal? So, for example, you might remember back in your elementary school days having your hearing tested, and they would put those giant headphones on, and you would have to listen for very soft noises, different pitches, frequencies you would listen for. Right, what those hearing tests are looking for is what is your absolute threshold for hearing. And if you can't hear a certain decibel level volume, or if you can't hear a certain pitch frequency, well, that might indicate a potential hearing problem. Right, same thing with vision. You might remember having your eyes tested when you were younger, or if you have glasses, contacts, going and consistently getting your eyes tested. Right, well, what they look at is like, well, what's the smallest stimuli that your eye can be able to see? It's looking for light reflected, and so how much light needs to be present within the area. Right, certain people have very good thresholds where only a little bit of a difference is there and they can hear it. For example, how much pressure do you need on your skin to feel touch? How much salt needs to be in the food for you can taste those differences, right? And so your absolute threshold tries to test your individual bottom level of what's the minimum you need to experience something. Right? Signal detection theory takes another opposite stance. Right? They do believe that they're bottom thresholds, but these bottom thresholds are fluctuating and they change. Right? Signal detection theory states sometimes we're in a heightened state of arousal or sometimes we're exhausted, and because of that, certain signals will pass by our ability to understand them. even if it's at a good level, and even if on another day I would clearly be able to hear or see that thing. For example, new mothers, they can hear the faintest little whimper, but if you take another woman who isn't a mother, they could hear that same noise within the room and not respond to it. They don't recognize it. Military veterans, when they're on patrol, they're very aware of loud noises or soft noises and anything that might indicate a threat. Right? Their heightened state of arousal or their previous experiences makes them more aware of these sounds, and therefore they quickly respond to them. We used this example earlier where you're at home alone by yourself. Has anyone ever talked themselves into thinking that their house is haunted? Right? You're so on alert that you hear little tiny creaks in your house. But what you don't know is your house makes those noises every single night. It's just the natural pressure as the outside temperature cools, the wood or the foundations of the house, they expand and they make noises. So it's normal. And so what signal detection theory states is that your threshold level, your bottom threshold level, changes depending on your experience with something, what you're expecting to hear, how tired you are, or how motivated you are within these scenarios. And so for humans, we can't really find the bottom threshold. All right, so one of your questions on the worksheet is looking at that comparison between absolute threshold and signal detection theory. All right, so compare what are some similarities between them, what are some differences between them, and then tell me which one did you like the best? Which one do you think makes more sense in explaining human sensory interaction? All right, what we could also look at is subliminal messages. All right, if I send a signal that will hit your threshold levels, but it's not enough to go to conscious awareness, can I influence the way that you think and behave? All right, we kind of addressed this back at the beginning of the year when we played all those backmasked songs. I have the link here. It's not going to work in the video, but if you go to the PowerPoint posted on the GC website, you'll be able to pull it up and play with it some more. Right, but hearing those songs played backwards, well, there were words there that you could hear, but only after you were told what to listen for. Right? If you didn't know what to listen for, but the words were still played backwards, do those subliminal messages impact the way that we think? And so research into subliminal stimulation tries to figure out how much does these minimum threshold levels, these minimum stimuli that our body is able to process, but it's not enough for us to get to conscious experience, how much is that going to influence us? All right, we do know that sometimes these subliminal messages can change the way we think. So experimenters did a study where they would flash up different images for just 57 milliseconds. All right, it's enough for our eyes to grasp and process the information. We know this from iconic memory, but it's too fast for it to be deemed important for conscious awareness, because again, iconic memory is very short. So what they did is they just flashed these images, and then after 15 minutes, they asked individuals if they could identify what images they saw. Right? 1 in 3 could identify it in that 15-minute mark, right? Even if they saw 20 different images. So what it does show is that we sometimes are capable of seeing and processing these subliminal messages without any conscious awareness. And it can play a small role in the way that we think and behave. It's called priming. Right? If we flood you with a lot of information very quickly, we're processing it on an unconscious level, and then it plays a role in the way that we think and behave moving forward. They did a study where they had participants read a passage, and in the passage it was either embedded with a bunch of words that indicated being elderly or a lot of words indicating being young and youthful. And then, after they read this passage, answered a few questions, they had participants walk down a hallway to collect their fee for doing the experiment. What they found is that the people who read the passage about a lot of old things, they walked markedly slower, about 45 seconds slower on average, than our youthful components. And so people who'd read about things that were youthful. Right? These subliminal words kind of change the way that they process things. A movie that kind of addresses this, and again, it's a fictional movie, but it does talk about priming and trying to influence the choices that people make, is the movie Focus with Will Smith and Margot Robbie. So if you're bored, I would check that out, but it does a good job about explaining those subliminal priming elements and how they do play a slight impact on the way we think and behave in later situations. All right. However, it doesn't work for most people. Again, only one out of those three recognized the hammer that was flashed in front of them. Right, so it's not really that powerful and it doesn't last that long. It's just a temporary change in thought patterns and behaviors. Back when we did our research unit, they talked about correlational studies and how we needed to do true experiments to see if those relationships are really cause and effect. So they did the study looking at listening to subliminal tapes to either improve your memory or improve your self-esteem. Right? They were getting subliminal messages underneath the audio recordings of that tape. But the only ones that actually had an impact on their behaviors were the ones that were labeled self-esteem and that had a self-esteem subliminal message, and those that were labeled memory and had a memory subliminal message. Versus if I gave you a memory subliminal message labeled self-esteem, well, you felt a boost in your self-esteem, but there was no real boost in your memory, which is what should happen. So these subliminal messages don't really last long-term in changing your behaviors and therefore might not be as effective as we would originally think or believe. All right, so if we have our threshold levels and we know we need this amount of stimuli, how much of a difference between them can we use to figure out that something has changed? There's that old tale about if you want to have boiled frog, you can't put the frog immediately in the boiled water, but if you take a frog and put it in cold water, it'll sit in that pot until it's slowly boiling to death. But the one that goes immediately into the hot water will try and jump out. Right? The frog can't tell the difference as the water temperature changes and grows over time. So what researchers are also interested in is the just noticeable difference. How much of a difference between two similar stimuli need to be present for us to be able to know that something has changed? For example, there are people that are super tasters, and they can tell a slight difference between two similar dishes and know that this one has more pepper in it and this one has more cream within it. Right? Musicians, they need to have a really good, just noticeable difference threshold so that they can tell when their instrument is in tune versus slightly flat or slightly sharp. So for example, if you're tuning your guitar, right, as you go through and try and get the guitar string back in tune, right, those little tiny twists on the string, how much of a twist do I need to make for you to be able to tell that tune, that pitch is getting more in sync with what it needs to be? Right? The bigger the difference, the bigger the magnitude between the two stimuli, the easier it is to tell the difference. So Weber's law tries to measure what's the minimum difference that needs to be present. Right? It's a proportionate percentage. If you look at this picture that you see here, if I'm giving you 100 grams to hold in one hand and 105 grams to hold in the other hand, difficult but possible to be able to tell the difference, which hand is heavier. But if I gave you the bottom one, where it's 200 grams and 210 grams, well, those weight differences, it's a little bit harder to do. If I was giving you 5 pages of paper to hold in one hand and 1 page of paper to hold in the other, that one's fine. But if I give you 100 pages of paper to hold in one hand and then 102 pages of paper to hold in the other hand, well, those proportions are so similar, it's going to be harder to tell the difference between them. And so what we find is that there needs to be a percentage difference for us to be able to tell those differences. And the bigger the weight value, the bigger the light value that's present in the environment, the harder it is to tell those slight changes because our brain is almost already saturated with the stimuli. So what Weber's law states, if I want to tell the difference between weight, I would need about a 2% difference for it to be detectable. For light, we need an 8% difference. Our sense of hearing is very sensitive, and so we only need a 0.3% difference to tell the difference between two different sounds. And so we use Weber's law to help us figure out what will be that just noticeable difference between these stimuli. What we could also look at is why do we ignore sensory stimuli in our environment even when we've responded to it in the past? All right, well, part of it might be sensory adaptation. All right, once we've been exposed to a stimuli and the signal's been sent over and over and over again, we know what our thalamus decides to do is sometimes filter out unnecessary information. So our thalamus, after receiving the signal consistently, processing it into a neural code so that our brain upper level regions can understand it, well, eventually it's going to stop sending that signal because it knows the upper level regions doesn't need that message anymore. For example, Febreze had this commercial where people have gone nose blind to certain scents, the smell of their car or their home. Well, what happens is they get so used to that smell that they literally can't smell it anymore. Their brain isn't sending that signal, and so they don't process it. If you go to the zoo and you walk into the ape house, right, it smells really bad when you first get in there, but eventually you don't smell it anymore. When we're at school, there's that AC unit that's constantly humming in the background, but most people get so used to it that they filter it out. Or if you're sitting on your desk, right, when you first sit down, you feel the pressure underneath you to know that you've hit the seat. But after you've been sitting for a while, you usually don't feel it anymore. Your brain stops sending that signal. So what sensory adaptation states is that we get so used to a consistent sensory signal that this signal stops being sent because it's deemed unnecessary, because it's this constant stimulation that might be overwhelming. And so our brain naturally filters that thing out because we don't need to respond to it anymore. Oh, my GIF isn't working. Well, if you go to the slides and you try to open it up, this eye is supposed to be blinking and moving, and it shows you what sensory adaptation does and why it can be sometimes bad. All right, our eyes are constantly moving, and that's what allows us to see. And so this constant movement prevents sensory adaptation. But if you prevent your eye from moving, if you force it to stare at a fixed point, well, what you'll notice is that things will start to become a little fuzzy, and then it'll become black. You won't be able to see it anymore, and then it'll become fuzzy again, and then it'll come back into focus. And so this image shows an eye that's blinking, and you see it's becoming fuzzy and then out of focus and then back into focus. Or if you want, why don't you stare at a wall, find a fixed point, and just don't move your eye, and you'll eventually experience it yourself. Try to prevent blinking because this delays the process, but you'll see how our eyes sensory adapt, and it actually will lead to a very short but temporary kind of blindness where that figure will disappear from your sense of vision and then come back into sight again. All right, what we also know is that our sensory experiences are constructed within our brain. All right, a lot of that was addressed in the video you just watched. All right, the reason why our sensory experiences are constructed in the brain is because of something known as parallel processing. All right, parallel processing means our brain separates out sensory signals into separate units. They're processed in different parts of the brain, and then they're put all together into a usable whole so we can make sense of it. In your occipital lobe, which is responsible for all your vision, well, you have parts of your occipital lobe that are just there to detect color, so you can figure out what the colors of the object are. There are sections that are built for motion, so you can see something that's moving, something that's formed, so what's the shape, what's the image that I'm looking at, and then depth, what's the distance or what's the 3 dimensions of this thing. And then it puts it all together into one flying bird that you can see. Right? So if you have damage to part of your brain, you might lose your experience of some sensory signals. At the beginning of the year in the bio unit, we watched Secrets of the Mind. And there was the case study of the man who had blind sight. He was legally blind, but he could still detect motion. Right? Well, what happened was that part of his brain was still processing the sensory signals. He could still tell if something was moving up or down. But the ability to tell color, form, depth, well, all of those regions of the brain were damaged, and therefore he could only respond to that one perceptual element. He couldn't see something until it started moving, because that one brain region was still able to send that perceptual element up to him. And so with our parallel processing, it works for all of our senses. Right? How do we break things down? Right now you're listening to my voice. which means there are a lot of elements of sound that you're processing separately. It's not just the words that I'm saying, it's not just the sentences that they form, but you're figuring out what's the voice that you recognize. And so, can you actually tell that this is Miss McNamara? It's looking at my emotional state. So, how do I sound like I feel? Am I happy? Am I angry? Am I bored? Am I tired? And so, you're putting all of this together into a usable whole. And so, it works with all of the other senses. So, I want you to pick one other sense and see if you can break down what are the basic components that are being put together so that you can actually see it. And now I want you to answer, what do you see in this image here? Write down a few brief words, phrases to describe, but can you identify what is presented in this image? And then what about this one? Take a few minutes and write down, describe what is present in this image. What do you see? And then finally, what is depicted in this image here? What do you see? What's the object being depicted? All right, and then once you've finished your work, go through and submit it. Don't forget to grade your free response from last class. If you have any questions, I'll be online on Zoom at 1 o'clock, or you can email me. All right, have a good day.